Composition. Our objectives are to combine functions using algebraic operations, create a new function by composition of functions, evaluate composite functions, find the domain of a composite function, and decompose a composite function into its component functions. Suppose f and g are functions. Two major ways to combine f and g and create a new function are arithmetically, such as f plus g, f minus g, f times g, and f divided by g, or with composition, as in f composed of g. We can do this regardless of the format of the functions, in table, graph, and equation formats. Here we have a table format example. Using the tables, find the values below. We have a table for f of x and for g of x. F plus g of 2 is defined as f of 2 plus g of 2. Reading off the table, we see that f of 2 is 7 and g of 2 is 4, resulting in 11. F minus g of negative 2. F minus g is f of negative 2 minus g of negative 2. F of negative 2 is 5 minus g of negative 2 is 6, and 5 minus 6 is negative 1. Fg of 2, which is f times g of 2, is the same as f of 2 times g of 2. F of 2 is 7, g of 2 is 4, and 7 times 4 is 28. F over g of 1 is defined as f of 1 divided by g of 1. F of 1 is negative 10. G of 1 is 0, which is undefined. We can do similar operations using graphs. Here we have graphs of f of x and g of x. Again, f plus g of negative 2 is defined as f of negative 2 plus g of negative 2. F of negative 2, we can read off, is 1, plus g of negative 2 is also 1. 1 plus 1 is 2. F minus g of 0 is defined as f of 0 minus g of 0. Reading off the graph, f of 0 is negative 2 minus g of 0 is 2. So we have negative 2 minus 2 is negative 4. F times g of 0. This means f of 0 times g of 0. F of 0 again is negative 2 times g of 0, which is 2, giving us negative 4. Now f over g of 0 means f of 0 divided by g of 0. F of 0 is negative 2 and g of 0 is 2. Negative 2 divided by 2 is negative 1. An equation format example. Let f of x equal x squared plus 3x and g of x equal 2x minus 1. Find the values below. In the first example, we have f plus g of 3. It helps to write this out as it's defined, f of 3 plus g of 3. Then we use our functions and evaluate at those inputs. The f function says to square the input and add 3 times the input. Then we're adding to that g of 3. G says twice the input minus 1. Simplify and we'll be finished. 3 squared is 9, plus 3 times 3 is 9, plus 2 times 3 is 6, minus 1. 9 and 9 is 18, plus 6 is 24, minus 1 is 23. So f plus g of 3 is 23. F minus g of 3, we start out similarly. We're going to write the definition, f of 3 minus g of 3. F of 3 is 3 squared plus 3 times 3. And now we're subtracting g of 3. We do need to be careful here because we need to make sure we are subtracting all of g of 3. So when we see that negative sign, make sure that you are using parentheses or otherwise changing your sign of the entire binomial as you're subtracting. We'll have a minus 2 times 3 minus a negative 1, making it a plus 1. Again, you can change the sign of everything in the g of x or use square brackets or parentheses and later distribute this negative sign. 3 squared is 9, plus 3 times 3 is 9, minus 2 times 3 is 6, plus 1. 9 plus 9, 18, minus 6 is 12, plus 1 is 13. Here, f times g of negative 2. Let's first write out the definition. This is f of negative 2 times g of negative 2. F of negative 2 is going to be negative 2 squared, be careful to put parentheses there, plus 3 times negative 2, and we're multiplying that by g of negative 2. G of negative 2 is 2 times negative 2 minus 1. We simplify inside the square brackets. We'll have 4 minus 6, negative 2, and negative 4 minus 1 is negative 5. So I have a negative 2 times negative 5 is 10. F times g of negative 2 is 10. Now, f over g of 2. First, write out the definition, f of 2 divided by g of 2. Then we'll find f of 2. F of 2 is 2 squared plus 3 times 2. We're dividing that by g of 2, which is 2 times 2 minus 1. Now simplify. 2 squared is 4 plus 3 times 2, which is 6. 4 plus 6 is 10. Divided by 2 times 2 is 4, minus 1 is 3, and then we have f over g of 2 is 10/3. We can use this same process to find new functions. In this example, let f of x equal x squared plus 3x and g of x equal 2x minus 1. Find the equation and the domain for the following. F plus g of x, remember, is defined as f of x plus g of x. F of x is x squared plus 3x. G of x is 2x minus 1. And we simplify. X squared plus 5x minus 1. F minus g of x is defined as f of x minus g of x. Again, we have to be just a little careful. After we've written f of x, we need to remember that we are subtracting all of g of x. So we're needing to subtract 2x and subtract negative 1, making that a plus 1. Again, collect like terms to simplify. F times g of x is going to be f of x times g of x. So we have x squared plus 3x times 2x minus 1. So I'll have 2x cubed minus x squared plus 6x squared minus 3x. When we simplify, we'll have 2x cubed plus 5x squared minus 3x. F over g of x is defined as f of x over g of x. We have x squared plus 3x over 2x minus 1. When we find the domain for these new functions that we formed, the domain for the first three, f plus g, f minus g, and f times g, will be the same domain. The domain is all real numbers, and then remove any numbers that cause f of x and then exclude any numbers that are not in the domain of f and exclude any numbers that are not in the domain of g. The domain of f is all real numbers. The domain of g is all real numbers. So the domain of f plus g, f minus g, and f times g is all real numbers, negative infinity to infinity. When it comes to the last function, f over g of x, finding its domain, we will borrow the domain that we found for the first three functions, but we also have to restrict where the denominator is not equal to 0. Here, if we had an x value of 1/2, that would cause our denominator to be 0. So we exclude the value of 1/2 from the inputs. The domain is going to be negative infinity to 1/2 with the parenthesis, union 1/2 to positive infinity. Notice that the method for determining the domain depends on the functions that we started with and how they are combined. For example, with a square root, we need to exclude values that make the expression under the radical negative. For a rational function, we need to exclude values that would cause us to divide by 0. Now we're at compositions. Let's take a look at compositions of functions visually first. A composition of functions uses an output of one function as the input, or the x, for another function to produce a new function. A composition of f composed of, this is your symbol for composed of, g of x is equal to f of g of x. F composed of g of x means f is made up of an ingredient of g of x. So we see here that the inside ingredient for the f function is g of x. The chain of events that happens is that we have some input. It is put into the g function, and out comes g of x. Well, g of x is then put into the f function, and out comes f of g of x, or f composed of g of x. A general note about composition of functions: when the output of one function is used as the input of another, we call the entire operation a composition of functions. For any input x in functions f and g, this action defines a composite function, which we write as f composed of g, such that f composed of g of x is equal to f of g of x. The domain of the composite function f composed of g is all x such that x is in the domain of g and g of x in the domain of f. Note, it's important to realize that the product of functions f times g is not the same as the function composition f of g of x, because, in general, f of x times g of x will not be equal to f of g of x. Let's try some function composition in equation format. Here I have f of x equals x squared plus 3x and g of x equals 2x minus 1. Find the following. For any input x in functions f and g, this action defines a composite function, which we write as f composed of g, such that f composed of g of x is equal to f of g of x. The domain of the composite function f composed of g is all x such that x is in the domain of g and g of x in the domain of f. Note, it's important to realize that the product of functions f times g is not the same as the function composition f of g of x, because, in general, f of x times g of x will not be equal to f of g of x. Let's try some function composition in equation format. Here I have f of x equals x squared plus 3x and g of x equals 2x minus 1. Find the following. F composed of g of 3. It helps to write the definition f of g of 3. As always in algebra, we're going to evaluate the inside first. So let's go ahead and write the outer shell, f with our square brackets, and g of 3 is 2 times 3 minus 1. We can simplify before we move on. This will be f of 5. Now, the only thing left to do is to take f of 5. F of 5 is 5 squared plus 3 times 5. 25 plus 15, we have 40. Now we have g composed of f of negative 3. This means g is going to be the outer function, and f the inner function, with negative 3 as the input for f. Again, we're going to evaluate the inside first. F of negative 3 is going to be negative 3 squared plus 3 times negative 3. So this is g of 9 minus 9 is 0. The only thing left to evaluate is g of 0. The g function says 2 times the input minus 1, and the result is negative 1. So g composed of f of negative 3 is negative 1. Now g composed of g of 6. This is g of 6. So again, we write leaving the outer function and work on the inside. G of 6 is 2 times 6 minus 1. Simplifying the inside, we have 11. G of 11 is the only thing left to evaluate. We have 2 times 11 minus 1, which is 21. Let f of x equal x squared plus 3x and g of x equal 2x minus 1. Find the equation and domain for the functions below. F composed of g of x. We'll write the definition. This is f of g of x. So we start on the inside. Instead of writing g of x, we write what g of x is, 2x minus 1. There's no simplification to be done, so we go to the next step of putting 2x minus 1 inside the f function. 2x minus 1 squared plus 3 times 2x minus 1. We continue simplifying. We'll have 4x squared minus 4x plus 1 plus 6x minus 3. And collect our like terms. 4x squared plus 2x minus 2. The domain for f composed of g is such that x is in the domain of g. The domain of g is all real numbers. And g of x is in the domain of f. The domain of f is all real numbers. So we have the domain of negative infinity to positive infinity. Let's do the same with g composed of g of x. Again, we write the definition, g of x. We'll write the outer shell and work on the inside. G of x is 2x minus 1. There's nothing to simplify in there, so we continue on to putting that into the g function. 2 times some input minus 1. The input is 2x minus 1. And we simplify. 4x minus 2 minus 1. So 4x minus 3. Again, we want the domain is going to be all x such that x is in the domain of g and g of x is in the domain of g of x. We have no domain restrictions here because we have no fractions. We have no even radicals. So our domain is negative infinity to positive infinity. We'll have a little more interesting example later on, but this is a good start. Decomposition of functions. Decomposition of functions is a mathematical technique where a complex function is broken down into simpler, more manageable functions. It's like taking a complicated machine apart to understand its individual components. This will be helpful in calculus when we're trying to find the derivative of more complicated functions using the chain rule. Another good skill to have is to be able to decompose a function that is the composition of two or more functions. Here we'll find two non-trivial functions, f of x and g of x, such that f of g of x equals the square root of x squared plus 1. I see we have an outer function, the square root of some expression, and inside that I see x squared plus 1. X squared plus 1 being inside means that that is the g of x function, since g of x is the function being put inside f. My outer function is going to be the square root of some input x. So let's go ahead and demonstrate that this works. We'll take f composed of g of x. I know by definition that is f of g of x. I'm replacing the g of x with x squared plus 1. And now when I take f of x squared plus 1, it puts it inside the square root function, and I have square root of x squared plus 1, which is what we had in our composition. Let's look at function composition in table format. The full values of f and g are shown in the tables. Let's find the values of, first, f composed of g of 3. Again, we'll still write out the definition. This is f of g of 3. We keep the outer shell and actually find g of 3. G of 3 in the table is 0. Now we find f of 0. F of 0 is negative 10. Now g composed of f of negative 3. This is g of f of negative 3. We keep the outer shell, the g, and f of negative 3 is 6. Now g of 6 is 3. Let's find g composed of g of 6. This is g of 6. So this is g of 6 is 3. G of 3 is 0. Consider the functions f of x equals negative 3x plus 1 and g of x equals the square root of x plus 4. Let's find f composed of g of x. Starting with the definition, f of g of x. F of g of x being the square root of x plus 4. Now we put this into the f function, and that is our new function made from a composition. Now what is the domain of this f composed of g of x? Well, we look at the inside first. That inside function is a square root of x plus 4. I know that x plus 4 must be greater than or equal to 0 for us to get real values out of that function. So x must be greater than or equal to negative 4. And when we look at the apparent function that comes out, there's no other restriction except for this x must be greater than or equal to negative 4. So the domain is negative 4 with a square bracket to positive infinity.